This section is about DFS or depth first search. So we are going to learn the concept of DFS and then what is DFS algorithm and some of the properties of DFS. Okay, this is the DFS. When we learn about the DFS, we need to understand subgraph. What is subgraph? If you learn about tree, we learn about subtree. Sub means part of something. So if it is a tree, then we will have subtree, which is part of the tree. If we have graph, so we will have subgraph. This is a part of the graph. So by the definition, subgraph S of a graph G is a graph such that the vertices of S are a subset of the vertices of G. The edges of S are a subset of the edges of G. So I can say if I have G graph like this one, I have 1, 2, 3, 4, 5 nodes or 5 vertices, and then I have 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 edges. Then let's say I just want to check the blue color. So this blue color, this is the subgraph, because the blue color they are also in the graph. So I can say S is the subgraph of G, subset of G. Spanning subgraph. What is the spanning subgraph? The spanning subgraph of G is a subgraph that contains all the vertices. So if the vertices, okay, vertices, but sometimes we call vertices as nodes. So if all the vertices, if we include all the vertices, but some of the edges are not included, then this is spanning subgraph. So the spanning subgraph is a subgraph that contains all the vertices. So if all vertices include in the subgraph, then we call it spanning subgraph. Connectivity. A graph is connected if there is a path between every pair of vertices. Okay. Connected means this node and this node is connected. This node and this node is connected. This node and this node is connected. It is connected. This is connected. This is connected. Because this is connected graph. A connected component of a graph G is a maximal connected subgraph of G. What does it mean? We call it, this is a connected graph or connected component, and we want to check this is a subgraph. Okay, this is a subgraph because some of the edges are not in. Then we want to know whether this is maximum or not. Maximum or not. If you look at this one, this is the connection between two vertices. 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 But no connection. Then this is non-connected graph. Okay. And then how many of connected components? We have 1, 2. So it is non-connected graph with 2 connected components. So this is the first connected component. This is the second connected component. So we call connected component of the graph. It is the maximal connected subgraph. So if we can find any connected like this, so we call this a connected component. If we can have a connected vertices like this one, then we call this is the connected component, or we call this is the maximal connected subgraph. There are some other concepts about the graph. We call it trees. So this tree is similar with the data structure tree in terms of figures. The figures is similar with the tree data structure. Okay, so if you still remember the tree data structure, but this is different. The tree data structure, it is different with the tree in the graph. They are different. What is the difference? You can see here. In the tree of a graph, some of the concept they call it FRE, tree. It is a tree in undirected graph. Undirected graph means the graph has no direction. We have the connection between the vertices, but no direction, such that T is connected. So this is connected. And T has no cycle. No cycle means there is no X that can go to its own node. There is no cycle. So if every node is connected and there is no cycle, we call it this is a tree in undirected graph. So this definition of the tree is different from the one of a rooted tree. Do you know what does it mean by a rooted tree? In the tree data structure, we have root, and then we have descendant. Okay. We have children, or we call it this is the parent, this is the child. Okay. And the upper section of the tree, we call it root. Okay. We have the internal, okay, and then we have the external node. So the external node, or sometimes we call it leaf. Okay. So this is the rooted tree. But in the graph, we are having different definition. So the definition of the graph or undirected graph is like this. A forest is an undirected graph without cycle. So in the forest, as you know, in the forest you can have many trees. So this is tree number 1. This is tree number 2. Maybe this is a single tree. So we can also say that this is only a node. The connected components of a forest are trees. So here is the connected component. We call it tree. This is also another connected component. We call it this is the tree. Then those are points. I think you already learned the spanning tree in the mathematics engineering mathematics. You learn about the spanning tree. So let's look at the definition again: spanning tree and spanning forest. So spanning tree of a connected graph. Okay. For this connected means every of the node is connected. Every of the node is connected. So if it is a spanning tree of a connected graph, it is a spanning subgraph that is a tree. So what do you still remember? What is spanning subgraph? Spanning subgraph means we have a subgraph that contains all vertices. Okay. So all vertices will be in. Then in this case, if I have this graph, I have 1, 2, 3, 4, 5. Then in the first spanning tree, I will also have 5 nodes or 5 vertices. But the edge will be between the spanning tree 1. This is another spanning tree, spanning 2. This is another spanning tree, and so on. So it means one graph can have many spanning trees. A spanning tree is not unique. Unique means there is no only one. So it means there will be many spanning trees. A spanning tree is not unique unless the graph is a tree. So if the graph is a tree, then it is a spanning tree. So spanning trees have application to the design of communication networks. So if we have this kind of tree, we can use this as a communication network. I want to connect between this node to this node. Then, okay, we can go to this. I want to connect between this node and this node. Then I can see the connection through the other nodes. Okay. A spanning forest of a graph is a spanning subgraph. That is a forest. So can you draw a spanning forest? There can be a spanning forest like this one. So we call this is an example of spanning forest. Because a forest is a collection of trees. So this is a tree, and this is another tree, and this is a spanning subgraph because there are nodes to represent this graph and they are forests. So using those definition, we can check what is depth first search. DFS, sometimes we call it DFS or depth first search, is a general technique for traversing a graph. You still remember traversing? Okay. In the tree, in the rooted tree, there are some traversing method. You still remember? In the rooted tree, okay, there are three kind of traverses. Okay. So in the rooted tree, they have their own method. If you still remember, we go to the external node and then we go to other node and then we go to the next node. So we have the in order and we have post and then we have pre. So in the graph, we also have the traversal or the way to check every node in the graph. So the traversal of a graph, we want to visit all the vertices and angles. And we want to determine whether G is connected. And we can compute the connected component of G. And we can also compute a spanning point. The DFS on a graph with n vertices and m edges take ON plus 10. So if you design the DFS properly, then the big O notation will be n plus 10. But it depends on you. The DFS can be further extended to solve other graph problems. So this is the basic DFS. This is the purpose of the DFS, but we can also use also DFS to solve other problems. For example, find and report a path between two given vertices. So if I know one node, so I can find the shortest path between the node. Okay, I want to find between two vertices from this vertex to this vertex. Then I can find a path where is the best path. Or I can use it for finding a cycle. You should remember what this cycle. Okay, in the previous slide, we learned about the simple path. We also learned about simple cycle. Okay. So if it is a path, then the first node and the end node will be different. If it is cycle, then the first node and the end node will be the same. The depth first is to grab what Euler tool is to binary tree. If we learn from the rooted tree, there is an Euler tool. We can use the same idea of Euler tool, but we can make it as a binary tree in the DFS. So this is the algorithm. There are two algorithms. First, we want to set up the DFS. G is the graph. We will input the graph. So in this case, the graph will be a collection of vertices and edges. The output will be labeling of the edges of G as discovery edges and back edges. Okay, so we will take a look what is discovery edges and what is back edges. So for all U will be the vertical of the graph. Then we will set it as unexplored. For all E from the edges, let's set them as unexplored. For all V in the vertices, let's get the label. If the label is unexplored, then go to DFS G, V. It means we are going to do this algorithm. Okay, DFS G, V. This one. Now, this algorithm has an input, a graph G, and a sub vertex V of V. So this is the sub vertex. The output is a labeling of the edges of G in the connected components of V as discovery edges and back edges. So we want to know where is the edges, whether it is discovery or back edge. The first time we want to set the V is visited, and then we are going to check the incident edges of V. Do you know what is incident edge? We have no, and we have edge. So if it is V, then this is the incident edge of V. If we have another X from V to another node, then because this is the incident edge of V. So we will check if the E is unexplored. So we check if this one is not explored. Then let's check. W is the opposite of V, E. So if it is unexplored, so we want to know the W. The W is the opposite of V based on the SE. So if we are using E of this one, then this will be the W. And then check if the label W is still unexplored, then let's check the label of E. So the label of E, if it is unexplored, we call it discovered. And then we go to the next node, which is from W, we find another node. And then this will be a new V, and then we will check another edge, and then we will check whether it is W. If we go to another edge, we will check whether it is W, and so on. Now we need to know that if the node, something like this one, if we have E and if the W has been visited. Okay. So if the W has been visited previously, so this E will be backend. Then we can say that this X If the ads return back to any visited node, then this will be backwards. So let's see with example. So this is the Python code. We have a DFS G U discover. G is the graph, U is the starting node or the starting vertex, and discover is a dictionary mapping. So I hope that you already learned the dictionary from the video that I give to you. We will check for every incident edges of U and put it on the E. So let's check the opposite of U from E. And let B the B. So if V is not in the discover, then discover V equals. And then return back to the function DFS. So let's see the example. So we have the UV, it is unexplored vertex, and then we have the color is blue. We have VV, it is the visited vertex, the color is yellow. And if it is unexplored, we call it UV. If it is a discovery edge, we call it DE, and if it is a back edge, we call it DE. So if it is unexplored, we just make it as a line. If it is discovery, we make it with an arrow. If it is a back edge, so it is a line with dash. Okay, this is dash with arrow. Now we have a graph. So using this graph, we will have two states. The first state is the node state, and the other state is at state. The node at the first time, every node is UV. What is UV? UV unexplored. So we have not visited the node. So unexplored, unexplored, yeah. Unvisited, unvisited, unvisited. And then for every edge in the graph, let's say, yeah, we want to start from A to B. And then the other edge is B, C, C, A, C, D, D, A, C, E, E, A. Every other edges are UE. UE is unexplored. So we can start. Let's assume we start from A and B. Okay. So we want to, because it is the first, let's make it as discovery. If this is the discovery edge, so this is the first A, and then we are going to B, then based on the algorithm, A will be checked as visited, and then B will be checked as visited. Okay. A will be checked as visited, and B will be checked as visited. AB, now it becomes DE. DE is discovery edge. So we discover that there is a connection between A and B. And then next, we start from B. So B is the starting node. And then we want to check what is the possible edge or what is the incident edge. What is the incident edge from B? The incident edge of B is this one. Then we put BC as D, discovery edge, because C has not been visited. C is still unexplored. That's why we can make this as discovery edge. Let's go to the next. We have A visited, B visited, C visited. A visited, B visited, C visited, and then we have AB is discovery X, BC is discovery X, and then let's start from C. Okay. Now C, we need to check what is the incident X of C. The incident X of C is, okay, one of the X, this one. But A has been visited. So if A has been visited, it means it is a cycle. So we do not want to have a cycle because DFS originally DFS originally is a path. We want to find the path for all vertices. If you have a problem about cycle, then yeah, you can modify the DFS. But originally, the DFS is for path. We want to find a path for all the vertices. Then if we can find a cycle like this one, we will make it as a path because we want to find the discovery path. And if there is an edge going back to any visited node, the name is back. That's why the C to A is back. Now, after we have the C to A, we can explore. There is another edge from C to D. So C to D and D is not visited. Oh, sorry. I need to change this one. Maybe this is So this one should be V. This one should be V. And then we want to check the incident of C. This is the first incident of C. And then this is the second incident of C. And D is not visited. Okay, because D is not visited, then we will make the C to D as discovery edge. And then D will be set as visited. Now, the next node will be D. Okay, D, we will check the incident. So this incident edge is going to A. A is visited. So A has been visited. Then the edge from D to A will be back. Now we will check, is there any incident edge from D? No. Then we will go back to C. If we return back to C, so we will check. C, the incident edge of C is going to E. E is not visited. Then, okay, we will consider this CE as discovery. After we have this CE as a discovery edge, Then we set E as visited, and then we need to check from E. Now we need to check the incident ads of E. The incident ads is this one, and it is returning back to A. And A has been set as visited. Therefore, EA is back. So the final state will be like this. Every node will be visited, and every ad will be labeled either discovery ad or back. So if it is back ad, it is an ad that return back to any visited node. In this case, it is only A, but in different example, there can be another. And discovery ads is an ads that will be able to be the boundary. Okay? Or we can make the path from A to D. We can make a path from A to E. Okay, then I will stop here. I will continue the next section on brains. Okay. Thank you very much for attending the class. We will on the